Okay, let's get right into this. We talk a lot about the cloud on this show. We talk about Kubernetes, we talk about serverless, we talk about, all these AI-driven operations.
Hmm.
And usually we talk about them like they're these magical, ethereal things that just float above us in the ether.
Right, like they're just pure concepts.
Exactly. But today, I want to take a shovel. I want to dig. We are going way, way down. Beneath all those comfortable layers of abstraction, we're going to the bedrock.
We are indeed. And honestly, it is about time because you can build the most beautiful, architecturally pure microservices application in the world. You can have the fanciest React front end.
Sure.
But if the foundation is cracked, or if you simply do not understand the soil that your house is built on, eventually it is going to sink.
And when it sinks, all those buzzwords,
Yeah.
they're not going to save you.
Not at all.
So today we are doing a deep dive into the Linux command line interface, the CLI. But before everyone tunes out because they think, oh, I know how to Synex and CD. Hold on.
Yeah, this isn't that.
We are not doing Linux 101. We're looking at a comprehensive journey, really, from the absolute basics all the way to advanced DevSecOps proficiency. We're working from two really dense, really technical guides here.
Yep, the first one is from command line basics to DevSecOps proficiency, and the other is the Linux DevSecOps Cadet learning roadmap.
And these aren't just reading material, are they? They're structured almost like a curriculum.
They're battle plans. That's what they are. They outline a whole learning path for modern engineers, and the core argument they're making is actually kind of controversial in the modern DevOps world.
Because
It's saying that to be a master of the cloud, you have to first be a master of the Linux kernel.
which feels a little counterintuitive, right?
Yeah.
I mean, let me play devil's advocate here for a second.
Please.
The whole marketing pitch of Docker, of Kubernetes, of Lambda functions is that I don't have to care about the kernel.
Right. Don't worry about the OS.
I just ship my code in a little box and the platform handles the rest.
Yeah.
Why are we trying to go back to the 1990s?
That is the marketing pitch, yes. Abstract away the complexity. But let me ask you this. When the abstraction leaks, and it always leaks, what do you do? When your Kubernetes pod keeps crashing with a generic error 137 and the logs are completely empty, what's your next move?
Well, usually, I'll be honest, I Google it and copy-paste something from Stack Overflow and pray.
And that is the passive user mindset, and that's exactly what we want to break today. The whole shift-left philosophy in security is about integrating security earlier in the development lifecycle.
Bake it in from the start.
Exactly. But you cannot secure what you do not understand. When you look at a Docker container, it is not a magic box. It relies on fundamental Linux primitive.
Things like
Container privileges, file system mounts, network namespaces. If you don't know the CLI, those are just buzzwords you type into a YAML file. If you master the CLI, those become actual tangible controls you can manipulate and secure.
So the mission today is to take the listener from being that passive user, the copy-paste engineer, and transform them into what the sources call an infrastructure master.
Yes, someone who can diagnose, automate, and secure the substrate itself.
Okay, so how are we going to tackle this? What's the map for today's journey?
It's structured really logically. We start with anatomy, the file system, and permissions, the bedrock.
Okay.
Then we move to the engine processes and signals, how to control what's running. After that, the glue advanced shell scripting for automation.
Right.
Then the nervous system, all things networking, and finally the synthesis. That's where we show how all these pieces come together to create the illusion of containers.
I like that, the illusion of containers. Let's start with that first piece then, the anatomy, the file system. Now, I open a terminal, I see folders, bin, etc., var. To me, it's just organization. It's where things go. But our sources argue that the file system hierarchy standard, the FHS, is actually a major security control. How can a bunch of folders be a security control?
It is. Think of the FHS not just as a filing system, but as zoning laws for a city.
The zoning laws, okay.
If you walk into a quiet residential neighborhood and you suddenly see a massive smoking chemical plant, you know something is deeply, deeply wrong.
Right. That's an immediate red flag. It doesn't belong there.
Exactly. The FHS defines what is allowed where. It's a contract. If you find an executable binary running out of a directory that's meant for text logs, you don't just say, oh, that's messy. You say, I might be hacked.
Okay, that makes sense. So let's tour the city then. Let's start with a weird one that I think always confuses people.
Yeah.
Bin versus utter bin. Why on earth do we have two separate places for our main programs?
Oh, this is a great history lesson. It goes back to the very beginning. We're talking the 1970s. Ken Thompson and Dennis Ritchie are working on the original Unix.
Wow,
They
okay.
had a PDP-11 computer, and it had a massive top-of-the-line hard drive of about 1.5 megabytes.
1.5 megabytes. I think my email signature is bigger than that.
It's nothing, right? So they filled up the main root disk with the essential operating system, but they needed more space for user programs, for compilers, for all the stuff that wasn't strictly necessary to boot the system.
So they needed another disk.
They bought a second disk, mounted it at the path user, which stood for user system resources, and they put all the extra binaries there. That's it. That's the only reason.
So the structure of a modern Linux system in 2026 is haunted by the ghost of a 50-year-old hardware limitation.
In a way, yes. It's a historical artifact. Most modern distributions are finally starting to merge them now, just using symbolic links to point everything to one place, but the structure remains.
That's fascinating. Okay, so let's move into some of the more dangerous zones of the city. Let's talk about etc.
The configuration core. This is where the laws of your server are written down. Shit config, passwords, sudoers.
So this is the control panel.
It's the absolute control panel. And in a DevSecOps world, we talk a lot about something called configuration drift, and etc. is ground zero for that.
Define configuration drift for us.
Okay. You use Terraform or Ansible to deploy a new server. It's perfect, it's pristine, it matches your Git repository exactly.
Infrastructure as code.
Right. 2 months later, it's 2 a.m., something is broken, and Dave from Ops logs in to fix it. He tweaks a setting directly in Jinx and then jinx.com to get the site back up. He's a hero, he goes to bed.
But he never commits that change back to the Git repo.
He never does. And now your running server, your reality, is different from your blueprint in Git. That's drift.
And the problem is when you have to rebuild that server from the blueprint.
6 months later, you redeploy the server from the original blueprint, and the site crashes because Dave's crucial fix is gone. Or, even worse, an attacker gets on your box and modifies etc. shadow to add a new user for themselves. If you aren't auditing the files and etc. for changes, you have no idea who's actually in control of your machine.
That's a scary thought.
Okay.
What about var? It stands for variable data. Logs, mostly. Sounds pretty harmless.
Logs, mail spools, print queues. Yeah, it sounds boring. But var is a time bomb.
A time bomb. How so?
Imagine your application goes haywire. It gets stuck in an error loop. Error. Database connection failed. And it starts logging that error. Let's say 1,000 times a second.
Okay, so the log file's going to grow.
It grows fast, incredibly fast, gigabytes per minute sometimes. Now, if you installed Linux the default way with just one big partition for everything, the root partition, what happens when var fills up?
The whole hard drive is full. The whole system runs out of space.
Exactly. And when the root partition is full, the operating system can't write critical files anymore. It can't create lock files. It can't create temporary sockets. The whole system just seizes up and crashes.
You just accidentally denial of service yourself.
You did. All because you didn't separate var.
So the professional solution here is proper partitioning from the start.
Yes. In any production environment, you should put var on its own partition. That way, if the logs fill up, okay, logging stops, that's bad. But the OS keeps running, the rest of the application is fine. It's all about blast radius containment.
That makes a ton of sense. Okay, now let's talk about the real danger zone that the guides highlight.
Ah, yes, the world-writable public playground.
I use Tmall all the time. I download scripts there, I unzip files there. It's my scratch pad.
And so do hackers. Because TMAB is usually writable by any user on the system, even the low-privileged www data user that your web server runs as, it's the perfect place for a dropper.
Or a dropper. What's that?
It's a small initial script used to download the real malware. So let's say I hack your web server, maybe through a WordPress vulnerability. I don't have root access. I'm just running as the www data user.
Right, you're very limited in what you can do.
I can't write to bin, I can't write to etc., but I can almost always write to Team. So I use that access to download my crypto miner or my rootkit into Team, and then I try to run it from there.
Okay, so how do we stop that? The guide mentions a hardening tip involving a flag called noexec.
This is one of the highest return on investment security changes you can possibly make. It's so simple. You mount the Team partition with the noexec flag.
Walk me through what that actually does. What am I telling the kernel?
You're telling the kernel, hey, for this specific part of the file system, the one mounted at Tampi, I don't care what the permission bits say, nothing is allowed to be executed from here, period.
So you can still write the virus there.
Oh, yeah. You can write it, you can read it, you can move it around, but the moment you try to actually run it, the kernel itself steps in and says, nope, permission denied. You have completely neutralized an entire class of attacks with one simple configuration flag.
And how do you actually do that? Where do you set this flag?
You edit a file called etc.flab. That's the file system table. It lists all your partitions. You find the line for tamp, and in the options column, you just add no exec. Then you remount it, and you're done.
That seems almost too easy. I imagine it must break some things, right?
It can. Some, let's say, poorly written installers or updaters try to unpack and run scripts from tamp. Those will fail, but that's the trade-off. Security always introduces a bit of friction. The correct answer isn't to lower the shield because of a bad installer. It's to fix the installer.
Okay, let's move to the folder that isn't really a folder.
Proc. This one always feels like the Matrix to me. It's just bizarre.
It is the matrix proc. Is a pseudo file system. None of the files or folders you see inside it actually exist on your hard drive.
So where do they come from?
They are generated on the fly, in memory, by the kernel at the exact moment you ask for them. It is a direct window into the kernel's internal state, but exposed in a way that looks and feels like files and folders.
And there's one specific file in there that the guide highlights as a major aha moment for security. proc.environ.
This is a terrifying file. So every process running on your system has a directory in proc named after its process ID or PID. If your web server is PID 1234, there's a directory called proc1234.
Okay.
And inside that directory is a file called environ.
And what's inside that file?
Every single environment variable that process was started with. Okay, stop right there, because I know exactly where you're going with this. We are told constantly by every 12-factor app tutorial, by Heroku, by Docker documentation, store your secrets in environment variables. Osexkey DB password. Put them in the environment so they aren't checked into your source code.
Right. And to be clear, that is better than hard coding them in the source code. But it's not the end of the story. If I can get any kind of access to your server, even as a low-privilege user, and I can run cat proc1234 environ, what do I see?
I see the database password in plain text.
In plain text, null bytes separated, but plain text. And here's the kicker. Depending on the specific OS configuration, sometimes you don't even need to be root to read the environment of other users' processes.
Wow.
Or even more commonly, if I hack your web application and get remote code execution as the web user, I can just read my own process environment. I can just dump my own configuration and send all those precious keys straight back to my server.
So the industry standard advice is incomplete, or maybe just wrong for high security environments.
It's insufficient. It's an anti-pattern for truly secure systems. This is the entire reason tools like HashiCorp Vault or AWS Secrets Manager exist.
How do they solve this?
They avoid environment variables. Vault can inject secrets directly into an application's memory at runtime or mount them as a temporary file in a RAM disk that disappears the moment the process ends. It avoids this billboard effect of having your secrets just sitting there in proc for anyone to read.
That really changes how I look at my .env files.
Yes.
Okay, let's shift gears from files to the people or the things using the system.
Yeah.
User management, we all know, don't run as root. That's day one stuff. But the guide brings up a specific group, the Docker group.
The most dangerous group on a modern system by far.
Why? I mean, I add my user to the Docker group on my laptop so I don't have to type sudo docker every single time. It feels like just a convenience thing.
It is a convenience thing that effectively grants you passwordless root access to the entire machine.
Okay, you have to explain that. How?
The Docker daemon, the service that actually runs the containers, runs as the root user. When you, as a normal user in the Docker group, talk to it via its socket, you are giving instructions to a root process.
Right.
So if I'm in the Docker group, I can run this one simple command, docker run-v.host, edit Ubuntu bash.
Let me parse that out loud. You're running a new Ubuntu container. You're using ev.host to mount the entire host machine's root file system into the container at a new folder called host. And then you're starting an interactive shell.
Exactly. Now, I am root inside that container. I see d to host, etc. That's not the containers, etc. That's the real hosts, etc. I can edit the shadow file, change the root user's password. I exit the container. I can now log in as root on the host machine.
So being in the Docker group is exactly the same as having passwordless sudo privileges.
Correct. And on a multi-user system, or worse, a CI/CD build server, if you give a developer Docker group access, you have effectively given them the keys to the entire kingdom.
This logic extends to the containers themselves too, right? The roadmap is very, very insistent about not running containers as root.
This is the default sin of the container world. By default, if you don't specify otherwise, Docker containers run their main process as UID 0 as root.
But it's root inside the container. It's trapped in that namespace jail. It's not the same as root on the host, is it?
It's not, ideally. The namespaces are supposed to contain it, but container breakouts happen, new kernel vulnerabilities are discovered, the barrier isn't perfect.
So it's about risk mitigation.
It's all about blast radius. If I manage to break out of a container that's running as root, I am now root on the host. Game over. If I break out a container running as, say, UID 1001, some random unprivileged user, then I'm just a random unprivileged user on the host. I can't do much. I can't install a rootkit. I can't delete critical system files.
So the fix is to explicitly create a non-root user in your Docker file.
Yes. Just add ren user add insu 1001 abuser, and then at the end, user abuser. It's literally 2 lines of code in your Docker file that drastically reduces your attack surface. It's one of the easiest wins in container security.
Okay, let's wrap up this anatomy section with permissions. Specifically what the guide calls special attributes. We all know shmod 777 is bad, but what about something like shmod 4755? That 4 at the beginning.
That 4 is the SUID bit. It stands for set user ID.
Okay, explain what that actually does.
Normally, when you run a program, that program inherits your permissions. If I, as a normal user, run the cat command, it can only read files that I have permission to read.
Makes sense.
But if a binary has the SUID bit set, when you run it, it doesn't run with your permissions. It runs with the permissions of the owner of the file.
And if the owner of that file is .root,
then for the entire time that program is running, it runs as root no matter who actually executed it. The classic necessary example is the password command.
the one you use to change your password.
Right. To change your password, the program needs to write to the etc shadow file. You, as a normal user, can't write to that file. So the password binary is owned by root and has the SUID bit set. It temporarily elevates its own privileges for that split second to do its job, and then it exits.
That sounds necessary, but also incredibly dangerous.
It is. Because if there is any bug in that SUID program, a buffer overflow, an injection vulnerability, any way to trick it into doing something it wasn't designed to do, you can hijack that temporary root elevation. You can escalate your privileges and become root on the system.
So how do we keep an eye on this? How do we audit for potential backdoors?
You use the find command. It's an amazing tool. The command you want is find evperm 4000.
What does that do?
It searches the entire file system from the root file for any file that has the SUID bit 4000 set. You should run this on your servers. You should know exactly what is on that list and why.
And if you see something unexpected?
If you see something like nmap on that list, run. If you see vim on that list, run far, far away.
Because if vim is SUID root, I can just run it, open etc shadow, and edit it directly.
You've got it. It's a root shell waiting to happen. An attacker will often copy a tool like bash to a hidden directory, set the SUID bit on it, and now they have a permanent root backdoor.
Chilling stuff. Okay, let's move from the bedrock to the heartbeat. Section 2, process management. The system is booted, the files are in place, now things are actually running.
And this is where the system comes alive. It's also where things get messy.
So first off, just observation. We have tools like TETS and TOP. What's the fundamental difference?
TEPS is a photograph, a snapshot. It shows you the state of all the processes on the system at the exact millisecond you hit the enter key.
Again, TOP.
TOP, or even better, its modern replacement HTOP, is a video stream. It's a dynamic, real-time view of what's happening. You can see CPU usage fluctuating, memory changing. It's a living view.
I do love HTOP. It's got the colors, the progress bars. It makes me feel like a hacker in a movie.
It's also just a much better user interface. You can scroll, you can kill processes right from the UI. It's a huge quality of life improvement. But the real master detective tool here, according to the guides, is LOSOF.
The LOSOF. List open files. Why is this considered the detective?
Because of that core Linux mantra. Everything is a file. That's not just to keep saying, it's a fundamental design principle. A text file is a file. A directory is a file. Your mouse is represented as a file. And crucially for us, a network connection is also represented as a file.
A socket.
Right, a network socket. So let's imagine a classic scenario. You try to start your web server, and it immediately crashes with the error. Error. Address already in use.
Right, something is already sitting on port 80 or whatever port you're trying to use.
Exactly. In a less transparent OS, you might just get frustrated and reboot and pray it goes away. In Linux, you become a detective. You use lsof itybeat8.
And what does that command translate to?
It says, show me the process that currently has the file open corresponding to network TCP or UDP port 80.
It returns.
It returns the process ID and the name of the command. Oh, look, an old Apache process is still running. Or, oh, look, I left a Python debug script running 3 days ago and forgot about it. You immediately identify the culprit. No guesswork.
Okay, so once we find the culprit, we have to deal with it. We have to kill it.
This brings us to signals, which the guide calls the language of control.
Yeah, most people just learn to type kill PID.
Or, if they're really angry and it's not working, kill Nakosa 9.
The nuclear option, right.
Hey.
But you need to understand what you are actually doing. Kill doesn't just kill. It sends a signal. By default, with no flags, it sends SIGTERM, signal number 15.
And what does SIGTERM say to the process? What's the message?
It's a polite request. It says, excuse me, could you please begin your shutdown sequence, wrap up what you're doing, and exit gracefully when you have a moment.
So it gives the application a chance to clean up after itself.
Exactly. A well-behaved application will catch the SIGTERM signal and use it as a trigger to finish writing data to the database, close its open file handles, and then exit cleanly.
And SIGKILL, signal 9, what's its message?
SIGKILL is not a request. It's a direct, unblockable order from the kernel itself. It says, you no longer exist. The process is ripped from memory instantly. There is no cleanup. There is no chance to save state. It's just gone. So why does this distinction matter so much in the context of something like Kubernetes? This felt like a really specific and important point in the guide.
Oh, this is a huge source of instability and slow deployments in the container world. So when Kubernetes wants to stop a pod, maybe you're doing a rolling update or scaling down, the first thing it does is send a SIGTERM to the main process in your container.
It makes the polite request first.
Right. And then it waits. It has a configurable grace period, which is usually 30 seconds. It waits for your app to pack its bags and leave.
And what if the app doesn't leave?
If your app is just a simple shell script or a poorly written Java application that doesn't properly handle signals, it just sits there. It completely ignores the polite request. Kubernetes waits, tick, 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 for 30 seconds, and then it gets impatient.
Then it sends SIGKILL.
Then it sends SIGKILL. So 2 bad things just happened. First, your deployment just took 30 seconds longer than it needed to for every single pod. And second, your application might have had its data corrupted because it got shot in the head mid-sentence instead of being allowed to finish.
Whereas if you write your application to handle SIGTERM correctly,
it could shut down in 200 milliseconds. Your deployments become almost instantaneous and, more importantly, safe.
There's one more spooky term in this section that I want to cover. Zombies.
A zombie process. You'll see them in top or IPs marked as defunct. They often have a Z in their status column.
Is it still running? Is it consuming resources? Is it eating brains?
It's dead. Completely dead. It's taking up 0 CPU, 0 RAM. It is just an entry, a single line, that's left over in the kernel's process table.
So if it's dead, why is it still there?
Because its parent process hasn't acknowledged its death yet. In Unix, when a process dies, it stays in the process table until its parent reads its final exit code. This act of reading the exit code is called reaping.
Okay, so on a normal server, who does this reaping?
The main init system. On modern systems, that system, it runs as PID1. It is the great ancestor of all other processes, and it acts as the grim reaper of processes. If a parent process dies before its children, those orphan children get adopted by PID1, and PIL1 reaps them immediately when they finish.
But in a container, things are different.
In a container, your app is PID1. If your entry point is a Python script, that Python script is PID1. And a standard Python interpreter is not designed to be a grim reaper. It doesn't know how to handle and reap orphan child processes.
So if your main application spawns other little helper processes, like shelling out to run a command, and those helper processes finish,
they become zombies. They die, but their entry remains in the process table because PID1, your app, never reaps them.
And what happens when you get too many zombies?
The process table, which has a fixed size, eventually fills up completely.
And then what?
You can't create any new processes at all. The container becomes useless. It can't even start a shell to debug itself. It effectively crashes.
What's the fix for this? It sounds like a really subtle but deadly problem.
The fix is to use a proper minimal init system inside your container. The most common one is called Teeny. You add it to your Docker image, and you make it your entry point. Teeny then becomes PID1. It starts your actual application as a child process, and its one job in life is to be a grim reaper. It handles the reaping correctly. It's such a small detail, but it prevents these bizarre random production crashes.
Let's move on to section 3, the glue. advanced shell scripting. Now, I'll be totally honest. I hacked together bash scripts. I Google how to loop in bash. I copy-paste the first answer, and I just cross my fingers and hope it works.
You and 90% of the world. But the goal of this section in the roadmap is to move from that mindset, from fragile scripts, to treating your shell scripts as production code.
And the core concept for that is what the guide calls the fail-fast mindset.
Yes. So imagine you have a simple deployment script. It does 3 things in order. 1, CD into a directory. 2, build the application. 3, upload the application artifact.
Okay, seems straightforward.
Now imagine step 1 fails. Maybe the directory got renamed in a recent commit. The CD command fails. What does a standard bash script do?
It just keeps going, right? It prints an error but moves on to the next line.
It does. So now it tries to build the app, but it's in the wrong folder. That probably fails too. And then it tries to upload, well, maybe an empty folder.
Yeah.
Maybe it finds an old artifact from a previous build and uploads that.
It's chaos.
Yeah.
You could deploy the wrong version of your code to production without even realizing it.
So we use what's called bash strict mode. It's a line you should put at the very top of every single script you write. Set UO pipe fail.
Okay, that sounds like a magic spell. Let's break those flags down. First, set E.
That means exit immediately on error. If any command in your script returns a non-zero exit code, which is the universal sign for an error, the script dies instantly. It stops the bleeding before it can do any more damage.
Some developers hate this, don't they? They say it makes scripts too brittle.
They do, because you have to be more careful. For example, if you use grep to search for a string and it doesn't find it, grep returns an error code and your script will crash. So you have to learn to handle potential failures explicitly. But for operations and security, I would much rather a script crash loudly than silently do the wrong thing.
Okay, what about set U?
Error on undefined variables. This is the great RMS saver, you know, the old sysadmin horror story. RMNA-RF MYVRBin.
Oh God, yes.
If the variable MYVR is empty for some reason, maybe you made a typo bash, we'll just expand that to RMRF bin. It tries to delete your entire system.
And set U prevents that.
It sees that MYVR is undefined, and it kills the script with an error before it even tries to execute the ARM command. It's a lifesaver.
And the last one, pipe fail.
This one is a bit more subtle. In a command pipeline like command B by default, bash only looks at the exit code of the very last command in the chain.
So if command A fails, but command D succeeds, bash thinks the whole line was a success.
That's right. Command A could completely fail, send garbage output to command B, and command D might process that garbage without error, and your script would just continue on thinking everything is fine. Pipe fail changes that. It makes the whole pipeline fail if any command in the chain fails.
So set UO pipe fail basically puts safety rails on your bowling lane. It forces you to be a better programmer.
It does. It moves you from hopeful scripting to reliable automation.
Let's talk about text processing. The guide calls out the Holy Trinity: grep, sed, and awk.
The forensics team.
The point here is that you don't always have access to a fancy tool like Splunk or Datadog. Sometimes, in an emergency, it's just you, a raw log file, and a crisis.
Exactly. grep is your filter. It's for finding lines that match a pattern. The guide suggests a great security use case: searching your application logs for password to see if you're accidentally leaking plain text credentials.
Simple but effective. Next up,
Sed is for transformation. It's the stream editor. You can use it to do find and replace operations on a file or a stream of data without ever opening it in an editor. Things like sed I sold value config.txt. It's essential for automating configuration changes in your CI/CD pipelines.
But then there's awk. Awk is the one that always scares me. The syntax looks like hieroglyphics.
awk is incredibly powerful. It's a full-on programming language designed for processing text. But 99% of the time, you're just going to use it for dealing with columns of data.
Okay, so let's use the DDoS detection example from the roadmap.
Yeah.
You've got a massive Apache access log. You suspect you're under attack. You need to find the top IP addresses hitting your server right now.
Right. And an Apache logline usually looks something like this. IP address .date gets some patch of HTTP 1.1/200. The IP address is the very first thing on the line, the first column.
So step one is to extract just that column.
Yep. You run awk print $1 access.log. $1 just means print the first column. Now, your output is just a massive long stream of IP addresses, one per line.
But they're all jumbled up and not counted?
Correct. So you pipe that output to the sort command. Now, all the identical IP addresses are grouped together.
Then you need to count them.
So you pipe the sorted list to unique C. The TASI flag tells unique to count the occurrences of each unique line. So now your output looks like 50, 192.168, 1.1, 123, 10.0.5, and so on.
But that list is probably still thousands of lines long and in no particular order of frequency.
So you add the final pipe, sort DNS NR, that's sort numerically and in reverse order.
So the biggest number, the highest count, bubbles up to the very top of the list.
And boom, at the top of your screen you see 15,432 requests from this one IP address. You've just identified your attacker in about 10 seconds using a single line of code without any expensive tools.
That is incredibly powerful. I would take that over clicking through a slow, clunky web dashboard any day of the week.
That's the speed and power of CLI mastery.
Let's move to section 4, the nervous system. Networking. This is always where the finger pointing begins. It's not my app, it's the network.
Or it's not the network, it's the firewall. Always somebody else's problem.
First off, let's do a tool check. If config, still a thing.
Dead. Deprecated for years. Don't use it. It can give you misleading information on modern systems.
Okay. What about netstat?
Also dead. Replaced.
So what are the modern replacements we should be using?
For network interfaces and routing, you use the IP command from the iproot2 suite. So iproot to see your IP addresses, iproot to see your routing table, and default gateway. And instead of netstat, we now use SS.
SS for socket statistics.
Right. It's much faster than netstat because it gets its information directly from the kernel and it gives you more detailed information. The one command you absolutely want to memorize is SS-tone.
SS-tone. So let's spell. What does it do?
It's a mnemonic. Show me all TCP and UDP sockets that are in a listening state and show the addresses as numeric instead of trying to resolve host names.
So it's a quick way to see every single port that your server is currently listening on.
Exactly. If you start your new web server and you run the ston and you don't see port 80 or 443 in that list, your server isn't running correctly, or it's bound to the wrong network interface. It's the first step of any network debugging.
Okay, now for troubleshooting. The guide suggests a systematic workflow. Don't just flail around. Be methodical.
Yes, you work your way up the network stack, layer 1 to layer 7.
Step 1, reachability ping.
Start with ping.
You mean
8.8, ping a public IP address. If this works, you know your server has a basic connection to the internet. If it fails, well, it's tricky. Many firewalls block ping traffic, the ICMP protocol. So a failed ping doesn't always mean the host is down.
Right. Step 2, DNS.
Now try dig.google.com. Did it give you an IP address? If ping by IP worked but dig fails, you have a DNS problem. In the Kubernetes world, this is critical. You dig my-service.default.svc.cluster.local. If that doesn't resolve, your internal cluster DNS is broken.
I've heard people say that 50% of Kubernetes outages are actually just DNS problems in a trench coat.
It's not far from the truth.
Okay, step 3, cord connectivity. The guide loves ISIACID.
This is the smoke test for firewalls. You run nc-zv 10 by 0.0.58.
The flags are NATZ40IO, which means just scan, don't send data, and ANDV for verbose output.
Correct. It tries to complete the three-way TCP handshake on that port. If it comes back and says connection to 10.0.5 port 80 TCP HTTP succeeded, you know the network path is clear. The firewall is open. If your application still doesn't work, the problem is inside the application itself at layer 7.
But if NC just hangs and times out,
then you know a firewall is blocking you at layer 4. That distinction, is it the firewall or is it the app, saves hours and hours of debugging and finger pointing. NC gives you the answer.
And what if the connection is just flaky? Step 4, packet loss. The tool here is NTR.
My traceroute. It's like ping and traceroute had a baby. It constantly sends packets and shows you every single hop between you and the destination, and it shows you the live packet loss percentage at each hop.
So you can see exactly where on the internet the connection is dying.
Exactly. You can say, oh, look, it's leaving my data center fine, but it's hitting 30% packet loss at this specific ISP's router in Chicago. It allows you to pinpoint the problem with incredible precision.
We can't talk networking without talking firewalls. IPTables. Just saying the word gives some people a headache.
The great and terrible IPTables.
It's notoriously complicated, but in a world of Kubernetes, it's pretty much unavoidable, right?
It is. When you create a Kubernetes network policy that says, allow pods with label A to talk to pods with label B on port 5432, that high-level rule gets translated by the CNI plugin into a set of low-level IPTables rules on the actual worker nodes.
So if you think your traffic should be blocked, but it's still getting through, you might have to get your hands dirty and dig into the IPTables chains to see the raw rules.
And you will likely see thousands of automatically generated rules. It's an absolute mess. But understanding the basic flow of packets through the chains, pre-routing, input, forward, output, post-routing, is sometimes the only way to debug why your network policy isn't behaving the way you expect.
Okay, this brings us to the grand finale. Section 5. the synthesis, containerization and hardening. This is the climax. This is where all the previous sections come together.
And here is the big secret, the main takeaway. Containers do not exist.
Sorry, I'm pretty sure I have Docker Desktop running right here. What do you mean they don't exist?
I mean, there is no primitive, no object in the Linux kernel called a container. It's a lie. It's a convenient user space concept that we've all agreed to believe in.
So what is that thing that starts running on my laptop when I type Docker run?
It's a regular Linux process, just like ls or vim or chrome. But it's a regular process that has been started with two very special kernel features applied to it: namespaces and control groups, or C groups.
Okay, let's break that illusion down. First, namespaces.
Namespaces are the walls.
Yeah.
They change what a process is allowed to see. They create an isolated view of the system.
Give me some examples.
Okay, the PID namespace. A process is started inside a new PID namespace. From its perspective, it is PID 1. It's the first and only process in the world. It can't see any of the other processes running on the host.
Then there's the mount namespace.
Right. It sees a completely different root file system. It thinks, etc., is the container zone private, etc., not the hosts, etc.
And the network namespace.
It gets its own private Ester network interface, its own IP address, its own routing table. It's completely isolated from the host's network stack.
So you're basically gaslighting the process. You're putting it in a small room with painted-on windows and telling it, this room is the entire universe.
That is a perfect analogy. And if namespaces are the walls of the room, C groups are the limits. They control what the process is allowed to use.
So this is where CPU and RAM limits come in.
Exactly. You create a C group and you say, any process in this group is only allowed to use 512 millibaud of RAM and 1 CPU core. If the processes in that C group try to use 513 millibaud of RAM, the kernel itself steps in.
And that's the infamous ohm killer.
The out-of-memory killer. The kernel's last resort. It finds the greediest process in the key group and sacrifices it to save the rest of the system. That's your error 137.
Understanding this, that a container is just a process with some walls and limits, gives us a superpowered tool that the guide mentions and center.
This is the Ocean's 11 master key tool. It lets you walk through walls.
Set the scene for us. Why would I need this?
Okay. You're following security best practices. You're running a destrol-less container image. This image contains only your compiled Go binary and its dependencies. There's no shell, no bash, no else, no curl, no teeps, nothing.
Great for security. If an attacker gets in, they have no tools to work with.
But neither do you. Your application starts crashing or it's not responding on the network. You try the standard Docker exec at my container bash.
And Docker says, error, executable file bash, not found in path. Because there is no bash.
You're completely locked out. You're blind. You have no way to debug what's happening inside the container.
Enter and center.
Ncenter stands for namespace center. You run this command on the host machine, not in the container. First, you find the PID of the container process on the host. Let's say it's 99999.
Okay.
Then you run a command like ncenter target 9999 netpid mount bin bash.
What does that do?
It starts a new process bin bash from your host, but it tells the kernel to run that process inside the existing network, PID, and mount namespaces of process 99999.
So my shell on the host, which has all my favorite tools like curl and TCP dump, has effectively stepped inside the container's isolated world.
You got it. You are using the host's tools, but you are seeing the container's processes, the container's network traffic, and the container's file system. You have bypassed the walls. You can debug the undebuggable because you understand the fundamental physics of namespaces.
That is unbelievably cool. That right there is the definition of moving from a passive user to an infrastructure master.
And there's one last piece of that puzzle for hardening: capabilities. We talked about how the old model of root versus non-root is too binary, all or nothing.
Capabilities are about slicing up the power of the root user.
Exactly. The Linux kernel breaks down the monolithic power of root into about 40 specific fine-grained powers. There's capchom, which lets you change file owners. There's capnet bind service, which is the specific power needed to bind to a port below 1024, like port 80. There's capsywise boot, which lets you reboot the machine.
So instead of running a web server container as the all-powerful root, you can run it as a normal, unprivileged user, but grant it just the one specific capability it needs: capnet bind service.
Yes. You use tools like capsha or Docker's capadd and capdrop flags. The absolute best practice is drop all capabilities, then add back only the one or two that your application provably needs to function.
So even if a hacker gets code execution inside that container and they try to load a malicious kernel module.
Permission denied. They don't have capsys module. They try to change the system clock to mess with certificates. Permission denied. They don't have capsys time. You have effectively defanged the root user, creating a much more secure, least privilege environment.
This has been a marathon. We have gone from 1970s hard drive limitations all the way to modern granular container security primitives.
We've mapped the entire terrain from the soil to the skyscraper.
So let's look at the outro. The roadmap divides this whole journey into 3 distinct phases for the learner.
Right. Phase 1 is confidence. This is about getting comfortable with the CLI. Learn the file system layout, understand users and permissions, stop being afraid of the terminal, and start seeing it as your most powerful tool.
Okay, phase 2.
Phase 2 is automation. This is where you master scripting, you learn your regular expressions, you learn grep, sed, and awk. You move from performing manual, repetitive tasks to writing robust, repeatable code that does it for you.
And the final phase.
Phase 3 is DevSecOps. This is the synthesis. It's understanding containers, auditing, and security pipelines. It's grasping the underlying kernel structures that make the entire modern cloud possible and secure.
The final takeaway from all of this, it seems, isn't about memorizing commands. It's about building mental models.
Yes, 100%. I don't know every single flag for the tar command. Nobody does. You look that stuff up.
XVF is pretty much all I've got burned into my brain.
That's all you need, really. The goal isn't trivia. It's visualization. When you type /user at host, you should be able to visualize the key exchange, the handshake. When you type Docker run, you should visualize the kernel erecting those namespace walls. When you understand the model, you can debug anything because you can reason from first principles.
I want to leave our listeners with one final provocative thought. We hear so much about noobs. We hear about AI writing our code and managing our infrastructure. Is the command line going to disappear? Is this all becoming obsolete?
I would argue the exact opposite. As we build these ever taller towers of abstraction, serverless AI platforms, manage everything services, the stack gets more complex, not simpler. And when those abstractions leak, when the AI hallucinates a firewall rule that opens a massive security hole, or the serverless function mysteriously hits a kernel file handle limit, who is going to fix it?
The person who knows what's happening at the foundation.
The person who can dig all the way down to the bedrock and see the truth. The abstractions make this deep knowledge more valuable, not less, because fewer and fewer people have it. You become the wizard. You become the one person who can actually explain why the magic suddenly stopped working.
That is a very powerful place to be. Listeners, grab those source guides we mentioned, spin up a terminal, and start digging. Because you can't secure what you don't understand.
Happy hacking!
We'll see you in the next deep dive.